Welcome to the third lecture of the course. In this lecture, we are going to develop or set up important notations and also one of the important tools which is fundamental to the whole of course. One is asymptotic notation, and also we'll have brief look at how to solve recurrences. So if you recall, we had a couple of recurrences during the last lecture. So let's just see how to approach them. So we'll start with the motivation for asymptotic notation. Okay. So let's consider the following scenario. Okay. So suppose we have a computational problem, whatever it is, and suppose there are four algorithms. Okay. So there are four different algorithm designers, and they came up with four different algorithms. Okay. So, and additionally, suppose the running times of these algorithms are as given below. Okay. So the first algorithm on inputs of length n or size n runs in time 500 n square. Second algorithm runs in time 2000 n square. Third algorithm runs in time n cube. Fourth algorithm runs in time n cube by 500. Okay. Now, so here our objective is to be able to compare these algorithms. Okay. So if you want to judge which is the best algorithm for your need or which is the fastest algorithm, so you need to be able to judge the running times, right? So let's make an attempt at comparing them. Okay. So which algorithm is faster? So, okay. Now I can easily see that for every value of n, algorithm 1 is faster than algorithm 2. No matter what value of n is, so n greater than 0, the running time of algorithm 2 is much higher compared to algorithm 1, right? Because 500 n square is smaller than 2000 n square for any n greater than 0, right? So there is a clear winner among the two. Now, if you compare algo 1 with algo 3, you can see that for n less than 500, algorithm 3 is better than, when I say better, faster than algorithm 1. But when n is large, algorithm 1 wins. That is, algorithm 1 is faster. Okay. So similarly, when you compare algorithm 2 with algorithm 3, you can see that for n less than 2000, algo 3 is better than algo 2, whereas for n greater than 2000, algo 2 is better than algo 3. Okay. So now I will not touch upon the fourth algorithm. I'll leave it to you to compare algorithm 4 with others as an exercise. Okay. So what does this say? Well, if you compare algo 1 with algo 2, there's a clear winner. Algo 1 is a winner. Whereas algo 1 and algo 3, there is no clear winner. Similarly, algo 3 and algo 2, there is no clear winner. Similarly, you can see that similar is a situation with algo 4. Algo 4 and algo 3 is a winner, whereas algo 1 and algo 2 compared with algo 4, there's no clear winner. Okay. So that is a problem, right? It's not clear how do we compare these four running times. Well, if you just take these two pairs, it is clear. Similarly, if you take these two pairs, it would be clear. But otherwise, across, it's not clear, right? So this is a problem, right? I mean, if you have two algorithms or if you have a set of algorithms, you don't know how to compare them. If there is no mutual winner, it's a difficult situation, right? Well, you can say that, okay, in real world, that it's a similar scenario. You may not have a clear choice always. But whereas here, I mean, this is something to be designed by us. So this is a world to be defined by us. So we should be able to compare them better. Okay, so, or just to pose questions, how do we compare performance of algorithms for the same problem or algorithms for different problems, or what is a suitable notion of efficiency? These are two fundamental questions, and we are going to address the first one here. The second one we'll look into it towards the end of this course. Okay, so let's, before telling a way of comparing algorithms or comparing the performance of algorithms, let's post our requirements first. Okay, so any such comparison, so what is a requisite quality? It should be such that any pair of algorithms should be comparable. Okay, so if you look at the previous example, algo 2 and algo 3, whereas as well as algo 1 and algo 3 are not kind of comparable, right? So there are domain, I mean, there are values of the domain, that is n, where for the, say for value up to 500, algorithm 1 performs better than algorithm 3. Whereas for n greater than 500, algorithm 3 performs better initially. When n is greater than 500, algorithm 1 performs better. Okay, so that is not acceptable. So we want a total order, that is every pair of algorithms for a given problem must be comparable. Okay, so whatever comparison that we set up should be a total order, and this should also be independent of input size. Okay, that is a fundamental feature, in fact, in algorithm design. Okay, so our comparison should not be based on input size. So for n equal to 100, okay, this is a comparison. For n equal to 600, this is a comparison. This is something not acceptable, particularly because you want uniformity. Okay, so an algorithm, if you have a running time which is basically given as a function of n, it should hold true for all n. Okay, maybe except a base case, which is fine. Say for except for n equal to 10 or n less than or equal to 10. That's at least fine. Okay, because you can come up with some brute force algorithms which works well for n equal to 1 to 10 in that case. Okay, so yeah, so these are our requirements. I hope I made sense so far. Okay, so now let's come up with reasonable candidates. Okay, so let's come up with a reasonable way of comparing. Okay, so let's look at our functions. Okay, so we saw that for certain values of n cube and n cube by 50 are smaller than 2000 n square as well as 500 n square. Okay, but if you just plot these functions, so as an exercise, I'll just ask you to plot. So I'll write an exercise here. So exercise. Plot these functions. So one of the simplest places, Wolfram Alpha online. Or you can use any of plotting tools. Okay, so if you plot these functions, eventually n cube and n to the n cube by 50 are going to dominate these functions. Okay, so if you plot the function, say for n equal to 1 to say 50,000, you'll see that these two functions start growing much faster than n square and 2000 n square and 500 n square. Okay, so in other words, for large enough n, so when the input size gets really large, the corresponding algorithms, that is algorithms having running times of n cube and n cube by 50 respectively, should be poor performers compared to the algorithms which have running times constant multiple of n square. Okay, so in other words, put a bit more abstractly, so any running time of the form alpha n to the a, where alpha is a constant, a is a constant, is better than a running time of the form beta times n to the b with b greater than a. It really does not matter what alpha and beta. So here it could be alpha is 1000, whereas beta is say 0.5 or 0.1 or 0.00001. Okay, but as n grows, this is going to dominate, or in other words, this algorithm will be performing far better than this algorithm eventually. Okay, so I'm sure many of you would have objections. You can say that, okay, so I live in a world where my n never goes beyond 100,000. Okay, so then, or maybe 50,000. Then isn't your comparison bad? Yes, that is true. So so when we develop theory, right? So we don't restrict the input size. That is a fundamental thing. Okay, so we want to take as n grows. That is, in analytical terms, n tends to infinity. Though this is not the right usage because these are not real numbers. These are natural numbers. So as n grows, and that is what we want to. So eventually is the thing that we want to say, or for large enough n. Okay, so for applications where you just want to study or develop an algorithm for n, say up to 100,000, our methods are not going to be useful. Okay, our methods are not for such things, which are more like ad hoc kind of algorithms, what we call as. So we will be looking at algorithms which works for all n, and the performance guarantees are for all n. That is all input lengths, or in fact all inputs. Okay, so with this in mind, now let's come up with a definition. Okay, a feasible notion of comparison. Okay, so to meet our requirements, one possible or feasible notion would be, so say two functions f and g. Okay, so we say that f is less than or equal to g. So I'm just abusing this notation. I'm not introducing a new symbol. I'm just writing less than or equal to. Okay, see, less than or equal to a relation which is defined over natural numbers or even integers or real numbers. Okay, I'm just extending them to functions in the following way. So I say that f is less than or equal to g if there is a constant n0, a non-negative integer constant, such that, so the value of f is bounded by value of g for all n which is sufficiently large. That is for all n greater than or equal to n0. Okay, so for values of n which is smaller than n0, we don't really bother. Say in the previous example, maybe n0 is 2000, or n0 is 5000, or n0 could be 20,000. Okay, so or n0 could be 1 million. So there is no limitation. It has to be a constant. It should not be a variable. Okay, it should be a fixed number. When you make this statement, it should be a fixed number. Okay, so now you can easily see that this defines a total order on all functions, but with one caveat. Okay, that represent running times of algorithms. Okay, so one just exercise would be exercise. What kind of functions represent running times of algorithms? Say sin x or sin n, would it represent running time? Well, not. Okay, so running time is something, as n increases, the running time should also increase. So it should be an increasing function. Okay, increasing function defined over integers or natural numbers should be the right choice. So I just leave to you to think about this. Okay, so the statement I made is This in fact defines the total order on all such functions. Okay. So, well, the reason is, I mean, so either f is above g or g is above f. Okay. So because it's a monotone function, so both are monotone functions. If one start growing faster than the other, they will it will keep outgrowing the other. Okay. So because the curve is only upward, I mean it will never come downward. So yeah. So basically this defines a total order. Okay. So let's not worry much about why it is a total order and all, but it meets a requirement. Okay. Yeah. So this is the exercise that I wrote. So why can't the running time be sin n? So, or what are the functions which represent running times of algorithms? Okay. So now with this definition, we have clear comparison between the four algorithms that we have discussed. I mean, whose running times we have discussed. Okay. So clearly algorithm 1 is dominated by algorithm 2, algorithm 2 is dominated by algorithm 4, and algorithm 4 is dominated by algorithm 3. So algorithm 1 would be the fastest with respect to our definition. Okay. Yeah. So aren't we done? So we have a method of comparison, right? Yes. We are almost done. Okay. Except that I'm going to do a bit more confusing thing now. I mean, so far I feel it is intuitive, right? This is fairly reasonable definition. So if you open any algorithm textbook, this is not the comparison they are doing, right? There's a slightly more, I would say, coarser notion of comparison that is done in the literature rather than this. Okay. Well, so let's call it as a variant of less than or equal to. Okay, it's pretty much the same. It behaves very similarly, but the notation is slightly different. So there are historical reasons and mathematical reasons for it. So let me tell what they are. Yes, it is the big O, which is for some people it's very nice, very happy thing, but for many it becomes a nightmare. Okay, it's the most confusing part. Okay, so I'll give you just brief reasoning why big O is needed. Okay, I mean, see, there is no harm in settling for this comparison, but like I said, the literature has its own reasons why it should consider a slight more, I would say, coarser notion or a variant, I would say, variant of this comparison. Okay, so let me formally define what is a big O notation. Okay, so let f and g be any two functions that represent running time. I just specifically said non-decreasing functions over natural numbers. So I say that f is in order of g. Okay, so this is one notation. Some of the books also say f is, so some books also say f is order of g. Okay, both notations are fine. I feel comfortable using in notation, okay, because it's mathematically more precise. Okay, nevertheless it does not really matter. So we say that f is order of g or f is in order of g if there is a constant c. So remember, when I say constant, it should be independent of n, and a number, again a constant, n0, such that f of n is at most c times gn. Okay, for all n greater than n0. So how does it compare with our previous definition? It compares well with our previous definition if we didn't have this constant. So we said f less than or equal to g if there is an n0 greater than 0 such that for all n greater than or equal to n0, f of n is at most g of n. All I did was put a constant multiple here. So allowed a constant. So C could be 100, C could be 1000, C could be 0.0001. It just that it should be non-negative. Okay, so this should be non-negative. So, or in other words, intuitively, we say F is order of G if F is less than or equal to G, where less than or equal to is the comparison that we defined a couple of slides earlier. F is less than or equal to C times G, where C times G is basically a constant multiple of the function G. Okay, that is C times G of n is C times G of n. Okay, so it's a function but a constant multiple of G. Or in other words, big O is essentially our relation that we have defined modulo constant multiples. Okay, so we allow equivalence up to constant multiples. Or in other words, constant multiples of a function are kind of considered equivalent with respect to this notation. They're all big O of each other. Okay, so for example, so 500 n square, 2000 n square, they're all in order of n square. Because if I take C as 500, 500 n square is less than or equal to 500 n square for every n, in fact. 2000 n square, if I take C here as 2000, so 2000 n square is less than or equal to 2000 n square, in fact, for every n. Okay, so similarly, if I take 1000 n square plus 5000 n plus 50, so we can show that this is order of n square. So let's see why. Okay, so let's consider thousand n square plus 5000 n plus 50. Okay. So now I can see that 5000 n is less than or equal to 5000 n square for all n greater than or equal to 5000. It's not equal to 1000 n square plus or okay, even simpler. So this is less than or equal to 5000 n square for all n greater than or equal to 1. And I can also replace this 50 by 50 n square for all n. Right? So this is 6000 50 n square for all n. So therefore 1000 n square plus 5000 n plus 50 is big O of n square. Okay. So what I did was, I mean, it was much simple here. So what I did was, I just upper bounded 5000 n by 5000 n square. Okay, which is valid for all n, in fact, right? So 50 is again upper bounded by 50 n square. So overall, the whole function, in fact, is dominated by 6050 n square. So if I take C as 6050, I see that my function, say f of n, is at most to C times g of n, where g of n is n square. So hence this. Okay. So let's see some more examples. So 1000 n square is in order of n cube. Okay, let's see why. So 1000 n square is less than or equal to 1000 n cube for all n greater than or equal to 0. Right? So therefore 1000 n square is in order of n cube. Yeah, it's fairly simple. Okay. So now let's see the second one. 1000 n square is in order of n cube by 10,000. Okay. So this is the first one. So the second one, 1000 n square is not equal to 1000 n cube. Okay. So this is less than or equal to c times n cube by 10,000 for all n greater than or equal to 0, where, so what is the value of c? C is 10,000 into 1000. What is that? 10,000 into 1000. So 10 to the 7. Okay. So I hope the notation is clear. In the tutorial this Friday, we will be discussing more examples on this. So don't worry if you still are confused with the notation. I hope at least the way we have introduced, it looks more natural than it usually does. Okay. So yeah, so second is a non-example. N cube is not in order of n square. Okay. So when you say, so okay, so this is a notation we need to understand. Okay. So this is a negation of the statement that we made, right? So let's go back and see the definition. So what is it? So we have defined when is f is in order of g. So when do we say f is not in order of g? So let's write it out. Okay. So let's just try to write it out. So I'm writing this out here. F is not in order of g if, so how do I write? So for every constant, there exists, so for every n0, there exists an n greater than n0 such that f of n is greater than c times g of n. Okay. This is a negation of this statement. Yeah, I'll just highlight this. Yeah. So now I hope it's clear. So if you take any constant c and a value n0, I can clearly come up with an n such that n cube is bigger than any constant multiple c times n square, right? Say for example, c is 10,000, okay? And n0 is say 100,000. So for any n which is greater than 100,000, you can see that n cube is bigger than 10,000 n square. And there is nothing special about this 10,000. You can take any other value for c. So for any other value of c, you can easily see that you can come up with a value of n for which n cube is bigger than c times n square. Whereas as long as c is a constant, that is important. Okay, I mean one can easily cheat by taking c as n, which is not allowed. C should be something which is independent of n. Okay. Yeah, so now we'll introduce related notions which are basically derived from big O notation. Okay, so the big omega notation. So big omega notation is basically the what do you say, reverse of big omega, big O. So f and g be any non-decreasing functions which represent running times of algorithms. So we say that f is in omega of g if there is a constant c and a value n0 such that f of n is, so look at the way inequality is written, f of n is greater than or equal to c times gn for all n greater than or equal to n0. So in the big O notation, it was less than or equal to. Now this is greater than or equal to. In other words, more intuitively, we say that f is omega of g if cg is, sorry, this should be c. So cg f is less than or equal to f for some constant c. Okay, that is f dominates cg for some constant. Or in other words, f is in omega of g, in fact, if and only if g is in order of f or big O of f. Okay, so sometimes we also call this as order of f instead of big O. Okay, so the traditional notation is big O, but we also end up using the term order of f. So this we'll say big omega, or for short omega of g. Okay. So yeah, so this should give you perspective. Okay, so this one says g is upper bounded by some constant multiple of f. In other words, f is lower bounded by some constant multiple of g. Okay, so they're essentially equivalent. Give you one or two examples. So yeah, clearly 100 n cube is omega of n cube. You can take c as anything, cs1, okay, or cs2. Okay, so sorry here, so it should have been omega. Okay, so you can also see that n cube is omega of n square. We'll see why. Okay, so what is the condition that is needed? So we need that there is a constant c and n0, right? So in fact, so for all n greater than or equal to 1, n cube is greater than or equal to n square. Therefore, with c equal to 1 and n0 equal to 1, we have n cube greater than or equal to c n square for all n greater than or equal to n0. Okay, so therefore n cube is in big omega n square. Okay, yeah, so please don't be confused with this set membership notation. Okay, so this is also, I mean, it's also fine to use equal to. Okay, so I won't penalize if you use equal to. Like I said, I mean, there is some mathematical reason why people use set membership notation rather than equal to, but it's not really critical. Okay, this is fine to use equality. Okay, so I hope so far it is clear. Just to recollect very quickly, so we introduced a way of comparing algorithms, performance of algorithms. We defined a feasible notion where all we needed was we say f is less than or equal to g, or algorithm running time f is better than algorithm with running time g if for sufficiently large n the running time of g is bigger than running time of f. Okay, and then we introduced big O notation. Now big omega notation, which is basically the dual of big O notation, essentially the same thing, but the functions are changed. Okay, and functions are swapped, in other words. So now we have another handy notation which we call as big theta notation. Okay, or big theta. So again, f and g be two functions. So we say that f is theta of g if f is order of g as well as f is omega of g. Or equivalently, we say f is theta of g if f is order of g as well as g is order of f. Okay. Yeah, this might sound a bit confusing. How is it possible? How is it possible that f is order of g as well as g is order of f? Okay. Yeah. So this example does it. So 100 n cube is theta of n cube. Let's see, why is that? So 100 n cube is less than or equal to 100 n cube. Therefore, with c equal to 100 and n0 equal to 1, 100 n cube is order of n cube. Okay. Now we want to say that 100 n cube is omega of n cube. And that's what we needed, right? We are using the first definition. Okay. So how do you see this? So take CS99, or in fact CS1. Why 99? Then 100 n cube is greater than or equal to n cube for all n greater than or equal to. Okay. So both are satisfied. That is 100 n cube is order of n cube with the constant multiple as 100, and 100 n cube is also omega of n cube with the constant as 1. Okay. So that way 100 n cube is theta n cube. Whereas you can see that, oh sorry, this again should be theta. Okay. Okay, this should be theta n square. So you can see that n cube is not theta of n square. Why is that? Because n cube is not big O of n square. But n cube is omega of n square. It's not big O of n square. So hence it fails. Okay. So yeah, so before we go into that, yeah, so let me just make a small remark here. Okay. I hope so far the definitions are clear. I agree that there are already too many notations. So big O, big omega, big theta. But I hope it is clear now. Big O and big omega are duals of each other. If big O as well as big omega, then it is big theta. Okay, so that's it. It's basically a handy notation for what we have. It's basically a combination of big O and big omega. But big omega is nothing but big O with the function swapped. So essentially we have introduced only one notation and we built on it for the other two notations. That's it. Okay. Okay, good. Yeah. So let me very, very quickly say what have we achieved with this big O, big theta notation. Okay. So all we did was the following. Okay. So this big theta notation, it basically classifies functions into equivalence classes. Okay. So this notation says that constant multiples of functions or multiples of a function are equivalent. Okay. So all we did was we took our less than or equal to relation, okay, where the same less than or equal to relation, we refined it further, or we made it not refined, I mean we made it coarser further by saying that two functions are the same if they are constant multiples of each other. Okay. So all constant multiples of a function are collapsed to one function. That's all we did with this big O, big omega, big theta notation. That's essentially what. Okay. So I'll leave it as a nice exercise here. Exercise. So define relation R on functions. When I say functions, functions which are non-decreasing defined over natural numbers as f r g if f is theta of g. Okay. Show that R is an equivalence relation. So R is an equivalence relation on set of all such functions. Okay. So in fact, one more small point I would like to make. Well, okay, I'll leave it to you. Okay, so if I do it, I mean, it already solves half of the exercise. Okay, so, okay. Yeah, I hope I'm clear so far. There's one more small notation, which I've just included it in the slide. I'm not going to explain it, okay? So you can skip it for now. When we need it, we'll come. So there is little o and little omega. It's basically big O and big omega, okay? With some additional constraint, okay? So let's just leave them for now, okay? So these are the examples of little o and little omega, okay? So we'll use this. I mean, we'll come to this when we need it. Okay, so that time we'll explain what it is. Okay. So in short, so we introduced big O, big omega, and theta notations. As a way of comparing running times. Okay. Now, so what is a primary feature? So where constant multiples of a function are considered to be equivalent. Yeah, I'll spend only 2 minutes on this. Okay, so this is something people always get confused. So how can you say that? I mean, it's the immediate question that you have is, so how can we say that algos with running times of n square and 1000 or say 10,000 n square are equivalent? Yeah. See, well, it's perfectly correct to say that it's unfair comparison, right? I mean, n square and 10,000 n square. Come on. So algorithm that runs in time n square is far better than algorithm that runs in 10,000 n square, right? So, but with our notation, they are equivalent. We don't, I mean, they basically theta of each other, right? So they're essentially in one equivalence class. So yeah, I would like to just mention here that, so this is done more because of the motivation from complexity. In fact, that is the only reason why we define it that way. Okay. So wherein, so the ultimate objective is to classify problems with respect to, say, their running time or any other resource requirements, where the computation model, which is Turing machine, so is so flexible that, so if you have any algorithm that runs in, say, time 10,000 n square, okay, you can convert this into an algorithm in the same model by simply modifying what we call as alphabets to an algorithm that runs in time n square. Okay, or in other words, if you have an algorithm that runs in 1 million times n square, you can convert them into an algorithm, convert that algorithm into an algorithm which runs in time n square for sufficiently large n, of course. Okay, so that it's called speed up. For those who are completely confused, well, I mean, come on, how can you do that? So intuitive way of reasoning is this. Okay, so now suppose I have a power to design a processor with arbitrary register size. So instead of 64 bits, I can use 1 million bits, suppose. Okay, then you can certainly reduce the complexity of a program, right, with the larger register. Well, there is a catch. I mean, I'm assuming you can do arbitrary function on a register, not just addition, multiplication, anything that you want to compute. So in that case, it is intuitive. The larger the word size of your computer, when I said word size, that is a register size, that is the bit. So you might have heard of 32-bit processor, 64-bit processor, and so on, right? So when this register size is increased, it's natural to expect speed up, right? So this linear speed up, which is done in complexity theory, is essentially such a speed up. Okay, so it just says up to constant factors I can always speed up. In real world, it may not be possible because it may not be feasible, technologically feasible, to come up with such large register computers, whereas mathematically it is feasible. Okay, so that's the reason why it is considered, and it's a traditional way. And there are many algorithm designers which don't agree with this. I mean, in the sense that their applications won't really admit such large constants. So then you'll try to come up with algorithm which is better. But for classification, for notational purpose, we'll be using this. Okay, so that's something that we need to keep in mind. Okay, so all constant multiples of a function are equivalent to each other for with respect to big O, big omega, and big theta notations. Okay, good. So let me check how much time I have. Okay. So I may have to stop the lecture now. I'll be recording one more video soon on recursion. Okay. So before the tutorial, so that it'll cover recursion too. So by tomorrow, I'll be uploading one more video. Yeah, so this is just to ensure that the length of video is small. Yeah, so if you have any questions, please shoot me an email. I'll be responding within a day. Okay. You can also post your question on Google group. So there is some problem in enrolling people into Google group. We should be able to rectify it by today. So we have added some 80 members. We'll be adding the rest today. Okay, so there were some I think problem with the emails entered and so on. So we'll just have a scrutiny and rectify it. Okay. So yeah. So this we end.